So 4.2 area, using sigma notation to write and evaluate sums, understand the concept of area, and approximate the area of a plane region. Find the area of a plane region using limits.
Does it sound like word problems?
So, no. There are words in them, but not specific word problems, I wouldn't say. So, sigma notation has a sigma, yes? What does it mean? What does sigma mean? You had it in pre-calc, you had in algebra 2. What does the sum? Okay, so we're going to be finding the sum. And we've got rules, and we will be focusing on some of those rules that will help us find the sum easier as we move through things. Okay, so I have the sigma from I equals 1 to 6. Remember, I is the index. It's just the variable, right? 1 is the lower limit. 6 is the upper limit. And from 1 to 6, there are how many things are we adding? 6.
Yeah.
How about from 0 to 5? How many things are we adding? 6. Because when that means we plug in 0, 1, 2, 3, 4, 5. So remember, the 1 to 6 is not how many terms, it's what number you plug into the function to get out, right? So the long way to do sigma notation is plug in 1 to I, so that'd be 1. Then we plug in 2 and 3 and 4 and 5 and 6, and then add them up. So that would be 7 and 7 and 7, so 7 times 3 is 21. Remember our trick with arithmetic, the little boy that didn't want to count everything? Okay, so now we're going to plug in 0, yes? So 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3 plus 1 is 5 and 6. What is my sum going to be? Isn't it going to be the same as the last one?
Yeah.
Yes. It's going to be 21. So can I write definitions differently and get the same answer?
Yep.
Okay, so the difference is one started at 0 and the other one started at 1. So did they have to adjust, making that 0 a 1? Yes. Okay, so the next one, what am I doing from 3 to 7? What's my equation? Oops. I'm squaring it. So I'm going to start at where? 3. And plug in till I get to 7. Okay. So I have 9, 16, 5 plus 6. Now, is the trick I used on the last one going to work? No, because it's not arithmetic. I'm not adding one thing. No, it won't. You can add them together, but am I going to get the same sum? No. But I can add them together, which I would do, because this would be 25, wouldn't it? Okay, and then this would be 50 with the 25. And personally, then I would do 70, 85, right? 36 and 49 would be 85. And then I would do 135. Oh, you were doing 50 plus 36? I try to find ones that are easy for my brain to think about adding, and then I add them up. Okay? That would take a long time if I had more than 5 things, wouldn't it?
Yep.
Yes? So we want rules and things like that. So what about this next one? Whoa, doggies. What's it say? Go 1 to n, so it goes forever, right? And it's 1 divided by n times k squared plus 1. So the n is always this upper limit, isn't it? So I got 1 over n, 1 over n, 1 over n, 1 over n, forever. But the k changes. So the k starts at 1 and then goes to 2 and then 3 and 4 and 5 and 6 and 7 all the way to n. So these are just different ways different things can be written. Got it? What does this mean?
Delta.
Delta. What does delta mean?
You know,
Change. Okay. So it just means change. So some of these formulas are going to look pretty hairy. But we're going to try to deal with them nicely. Okay, let me know you're good. Okay. Oh, wait. What was I going to say over here? Oh, when over here, I'm sorry, guys. Could I factor this n, 1 over n, out of all of this and then add up the rest?
yeah.
Yeah, because they all have it. So there's methods that can make it a little easier, right? So we'll just look for those. Okay, some rules that I have. Summation properties. When we have a constant, just like our integral, we can bring our constant out front. We can factor it out. See that? Again, on the last problem that I just showed you when I went back, that 1 over n, I would factor it out and then add everything up and multiply it by 1 over n. Makes sense? Now, I also know that I can break things up. So if I have the sum of a plus b, I can break it up to the sum of a plus the sum of b. When I keep my numbers smaller, do I tend to do things a little bit better? Yeah. Okay, so what I have down here at the bottom are some rules. They will make your life much, much easier. So I have the sum of a constant. Well, you just take the constant times the upper limit. When I start at, what do you notice all these start at?
1.
What? These rules don't work if it starts somewhere else, okay? So the second rule, if I have I from 1 to n of I, just like if it was an x, this is the equation I have. N times n plus 1 over 2 will give me the sum without plugging everything in and having to add it up. Think that will work out better? Yes?
Yep.
Okay, if it's squared, I have n times n plus 1 times 2n plus 1 over 6. A little bit more cumbersome, but if it saves me from plugging everything in and adding it all up, probably going to be more efficient. Especially if it's like 1 to 83, right? The last one we have on here is I cubed. So it's n squared times n plus 1 quantity squared over 4. Okay, so we're going to use our rules, and we're going to make things easier. So we need to evaluate the sum for 10, 100, 1,000, and 10,000. And that does not fit any of my rules that I just gave you, does it?
No.
Nope. But could I separate that into, could I make it the sum from I equals 1 to n, not equals, of 1 over n squared plus, that's an I over n squared plus 1 over n squared? Could I do that?
Sure.
Yes. Okay. Could I also make it the sum from I equals 1 to n of 1 over n squared times I plus 1? Could I do that?
Yeah.
We do that all the time with our fractions, don't we? Which one looks better, the left or the right?
Right.
The right. Looks much better, doesn't it?
Yep.
Okay, so are there good ways to rewrite things and bad ways to rewrite things?
Yeah.
Yes. Okay, so we're not going to do that first one. But it is an option. We could do it. I just don't want to do it. Okay, so now what happens is 1 over n squared going to be a constant?
Yeah.
Yes, because n is n. So what happens to a constant?
Here. Go to the front.
It goes in the front. So 1 over n squared, the sum, that's a sigma evidently. And this is addition, so can I separate it? Yeah, I know why I was doing that. So the sum of I from I equals 1 to n plus the sum of I equals 1 to n of 1. Now, why did I put the brackets around this?
Is it function or function?
Yep. It goes to both, right? So, does the sum of I fit one of our rules?
Yes.
It does, doesn't it? Okay, which one?
The second one?
The second one. So we have 1 over n times, the second rule says n plus 1 over 2. And does 1 fit one of our rules?
Since that's the constant, wouldn't it fit one? The first rule?
The first rule, and it says the constant times what?
The
N. And it's a 1. So 1 times n would be what? N. Do you want me to write 1 times n so you can see it just... Okay. So if that was a 2, it'd be 2n. Make sense? Okay. So I probably should get common denominators and combine that stuff, yeah?
Yeah.
So n would be 2n over 2. And this would be n squared plus n. Oh, I forgot my squared on my outside. So I have 1 over n squared times what? N squared plus n plus 2n is
N squared.
n squared plus
3.
3n all over 2. Okay. So we're still rewriting to make our life easier, yes? So what do you notice about your numerator?
It's a fraction.
The numerator isn't a fraction.
It's a constant.
No.
There's 2 n's.
There's 2 n's, so could I factor out an n?
You sure can.
So I have 1 over n squared times, actually, times n times n plus 3 over 2. So can I simplify that a little bit more?
No.
I want to give Ainsley a heads up that we're doing a fire drill at 10:30, so that you first don't.
Thank you.
Oh, man.
Okay.
Hey, at least we're on second floor.
Can I reduce one of these ends out?
Yeah.
Yeah. So I now have n plus 3 over 2n. So we've done all that work, and now all we have to do is plug in what?
Our numbers. 110, 100, 1,000, and 10,000.
Okay.
Why are we not doing things like yesterday?
You will.
We will, Jamie.
We're going to use yesterday's to make this easier.
No comprendo. Yeah.
So we're going to do it the long way, then I'm going to say, oh, but we could do it this way.
Why? That just makes it really confusing.
Sorry, that's what they tell me I got to do. Okay, so for n is 10,000, or n equals 10, I'm pretty sure that's what, 13 over 20?
Yep. Yep.
So n is 100.
$103 over 200.
Okay. And 1,000.
$1,003 over 2,000.
10,000.
10,003 over 20,000.
Okay, now, guys, do we know a way that if I have an equation, I could use my calculator and make a table really quick and not have to do all that work? Can't I put this into y equals and these as x's? And go to table set, ask, and plug in 10, 100, 10,000. Yes? Okay, so set this up. Use your calculator after that. Okay? This was pretty easy, right? 10, 100,000, 10,000. And we got fraction answers. They've got decimals. They'll probably say, give me a decimal. I don't know. The book usually wants a decimal, doesn't it?
Sometimes it says write a fraction or a decimal, but don't round up with the decimal.
Oh. Okay, so we would put this equation into y equals x plus 3 divided by 2x. Is that the equation we just found? Yep. And then we would go to table set, change it to ask, and put in 10, 100, 1,000, 10,000. And our fractions would be, our decimals would be 0.5, 0.51, 0.5015, 0.50015. What do you think 100,000 would be?
100,000. There's another 0.
It would just be another, actually 2 zeros, wouldn't it?
500015.
So it'd be 4 zeros in the middle?
Yep.
Okay.
Thanks.
Oh, look at that.
A beautiful transition.
So, what is my limit?
500,000.
Not 5. 0.5. Because I'm adding more and more and more and more zeros, you're getting pretty close to just a half. Oh, that limit word. Okay, approximate the area of the plane region using 5 rectangles. Here's the figure. Okay, now, the region is round, correct? Let's talk about it before we do any work. The region goes like this, yes?
Yep.
So it's like a fourth of a circle, maybe? Or a fourth of a oval, or whatever they call any general circular shape. So when you're putting rectangles in there, do you have some leftover stuff?
Yep.
Okay, so if I took these rectangles, how would I, find an area of a rectangle?
Length times height.
Length times width, or length times height, or width times height, whatever, right? So that's what we would use. Okay, and it says use 5 rectangles. Find 2 approximations of the area region lying between the graph of negative, okay, so it's a parabola. Yes? Negative x squared plus 5. This whole shape, if I saw it all, was a parabola. Okay? And it's from 0 to 2. So I only want from 0 to 2. And it said 5, so you from 0 to 2, you divide it by 5, and you get 2/5. Yes? So 2/5, 2/5 plus 2/5 is 4/5, 6/5, 8/5, 10/5. Do you all see how the numbers are happening? Okay. So we have right-hand approximations and we have left-hand approximations. So if we make rectangles from the right limit, it's under. From the left, it's over. And then you can kind of, I'll show you left hand. That's what left hand would be. See that? This is from the right of each of those two. Go back. We've got to understand what's going on before we do any work. So we have 2/5, 4/5, 6/5, 8/5, 10/5. So from the right, we went up and drew a rectangle backwards. See that? Up, back, up, back, up, back, up, back. So that's going to be an under approximation, correct? So then when we do the left, when I go up and over, what am I having over here? Do I have extra? Yes? Yeah. So if I took the extra minus the under, should I get what I'm looking for? Pretty close?
Yeah.
Okay, so that's where we're going with this. So we're going to come back over here. So my width is 2/5. This is 2/5. This is 2/5. This is 2/5. This is 2/5. And this is 2/5. Everyone understand that? Like my width is 2/5, correct? Is my width changing?
No.
No. Is my height changing? Yes. So we are going to find the sum of, and we want area, so we said width times height. We're going to use width times height. Length times width times height. All those words mean the same, right? What is our width? 2/5. Yes? How do I find my height? My height is on this curve, isn't it?
Guess an estimate.
Nope.
Time.
Okay. If I have an equation and I have an x value, plug it in. Yes? Okay, so I'm going to have 2/5 times you guys want I, you want x, what do you want? X. Actually, it would just be, trying to think how I want to write that. I want to say to put this in to this equation, right? So wouldn't it be negative 2/5 n squared plus 5? Because how many pieces do I have? 1, 2, 3, 4, 5. So it'd be from, you guys wanted x, didn't you? I'm going to use an n for right now to show you why. So we had how many? 1, 2, 5, because we had 5 pieces. If I plug in 2/5 times 1, I get what? 2/5. 2/5 times 2, I get what? 4/5. Our equation, we're going to just finish this side of it. So we have our equation. So let's go back over it. Where did we get the 2/5?
From
Width.
The width. Every single one of them is 2/5. Where did this come from?
You plugged it into the f of x.
I plugged it into the f of x right here. Okay, so everything is 2/5 times the n.
Oh, okay.
The first rectangle, the second rectangle, the third rectangle. So to calculate this, the 2/5 would go out. Yes? And then I would separate these two things. So I have 2/5. The sum of negative 2n squared. Nope. That's wrong. Wouldn't this be 4 over 25
Adios.
n squared?
Yeah.
Yes? Plus the sum of 5?
Yeah.
And then I would just find the sum. Okay, so on those, it's going to ask you for a left and a right hand. If you guys just want to do the right hand for now.
Like just like that.
Yeah, just like this. I'm fine because I haven't showed you the left hand yet. Okay? So if you want to look at just the right hand. Got it?